We're going to start our journey into combinatorics. But before we talk about that, just a quick recap of what factorial notation and what its actual definition is. And it might not quite be what you think it is. That is the definition of factorial notation. Okay? 0 factorial is defined to be 1. So often the question is asked, why is 0 factorial 1? Because it's defined to be 1. That's why it's 1. And then n factorial is simply n times n minus 1 factorial. It becomes a recursive formula. That is the definition of a factorial. So what does that mean? It means then we can now work out that 1 factorial is 1. Because it is 1 times 0 factorial, which we've defined to be 1. 2 factorial then becomes 2 because it's 2 times 1 factorial, which we've now worked out was 1. 3 factorial then becomes 3 times 2 factorial, so it's 3 times 2 because we worked out that 2 factorial was 2. So 4 factorial, 4 times 3 factorial, we've worked out 3 factorial is 6, so we get 24, and so on and so on and so on. What that then means is n factorial, which we said was n times n minus 1 factorial, we then could what we call roll out the factorials. So that would become n times n minus 1 times n minus 2 factorial. And if we keep rolling it out, we go all the way to 1, and this is what people think of as the definition for n factorial. And essentially it is. Because once you roll all those factorials out, that's what you're always going to get. All of those numbers multiplied together. But what that allows us to do is things like this, without a calculator. 12 factorial or 9 factorial, well, I could roll out that 12 factorial. It would be 12 times 11 factorial. But the 11 factorial would be 11 times 10 factorial. And we keep rolling it out until we can cancel the factorials. The 9 factorials cancel, so it's 12 times 11 times 10, 1,320. Now, the reality is I wouldn't write all of those lines in. But that's what we're doing when we're cancelling factorials. I get something like this one, 16 factorial and 10 factorial, 7 factorial. Okay, I will roll out the 16 factorial until I hit one of the ones on the bottom. So I'm going to hit the biggest one, of course. The 10 factorial would then cancel. If I write what I'm left with, I have this, again, without the calculator. This is great fun. Watch this. 7 times 2 is 14. Excellent, that means I've got this. Hang on, 5 3s are 15. Brilliant, I've got this. Hang on, 6 goes into 12 2 times. And 4 goes into 16 4 times. I've now got 4 times 13 times 2 times 11, which is, there it is, 1,144. But of course, that idea, you've got calculators that can do that, fine. But we can apply it to algebra. Now, your calculator's not going to do that. But we apply that idea. I've got an algebraic fraction with factorials in the bottom of the fraction. I want to get the common denominator. But remembering that k factorial rolls out, then I can get all the factors. It's k, k minus 1, and then I've got this factor of k minus 2 factorial because I've rolled out the k factorial. What's different? Well, the first one, well, it's the same. It is k factorial, so I've got the 1, even though I've put it second there. The k minus 2 factorial, what's different? Well, I've multiplied it by k, k minus 1, so that goes on the top. Tied it up, and that's the best I can do. Nothing's going to cancel there because k squared minus k plus 1 does not factorise, does it? No. So there'll be no factor there that I could possibly cancel. So that's a bit about factorials. Let's now get into combinatorics. The whole idea about combinatorics is counting. You see, we looked at probability, and the reality is all we're really interested in is how many things are in the spaces, not necessarily what they are. Because if I want to work out probability, it's the amount I want to know. So I want nice, neat, efficient ways of counting the objects without having to list them all, without drawing tree diagrams. I mean, they're still useful tools, but when you start talking about big numbers, you know, those branches, you know, hundreds of branches, it's just not efficient. So we want to come up with efficient ways. And the very first idea is this. It's a basic idea, hence why we call it the basic counting principle. If you've got one event and it can happen m different ways, and then after that you have another event which can happen n different ways, and the number of ways the two events can occur together would be m times n different ways. Simple idea. So I want to roll 3 dice. And by the way, when you roll 3 dice, it doesn't matter whether you roll them one at a time or all 3 at once. It doesn't change the number of outcomes. You could think of it as rolling them one at a time rather than rolling all 3 at once. So how many different ways are there? How big would this sample space be? Well, it would be this, 6 times 6 times 6. Why? Alright, I roll the first one. There are 6 different things that could happen. I roll the second one. There's 6 different things that could happen. I roll the third one. There's 6 different things that could happen. 216 ways. I know. Imagine if you were going to write them all out. That's going to take some. So in general, look, if you've got n distinct objects, but each of them have the same number of ways, then it's going to be n to the power of k, like I had here, 6 to the power of 3. So that could save some time too. How many ways can they show the same number? Well, now it's going to be 6 times 1 times 1, because think of rolling it one at a time. I roll one, well, I can come up with anything. So there's 6 different ways. But now I roll the next one, it's got to be the same as the first one. So there's only one way. And then the next one way. There are 6. Okay, you might have logically thought, well, of course it's 6, they all show the same number, there's only 6 different numbers. It's just a different way of thinking. So I can apply the thinking to any type of problem. It then brings up the logical next question. Well, what's the probability that all 3 show the same number? Okay, wow, 6 out of 216. I know the size of those spaces now. And that simplifies down to be 1 in 36. Here's a really nice HS. It's a very old HS. How is that? It's almost, 30 years? Gosh, very old question, but it's a nice question. Mice are placed in the centre of a maze. The maze has 5 exits. So each mouse is equally likely to leave the maze through any of the 5 exits. Thus, the probability of any given mouse leaving by an exit is 1 in 5. We're going to put 5 mice in there, let's just call them A, B, C and D. And they behave independently. So one mouse is not going to, oh look, that mouse is going that way, I'll follow it. No, they're totally independent. They decide which one they're going to go through. What's the probability that A, B, C and D all come out the same exit? Well, it's a probability question, so I need to know the whole sample space. So the first thing I work out is how many possibilities. It's going to be 5 to the power of 4, because each of those mice have 5 different exits they could go through. So 5 times 5 times 5 times 5. Okay, now it's out of 625. But how many ways could they all go through the same door? Again, logically you come up with 5 because there's 5 different doors, or you think about it this way and you say, well look, the first mouse can go through any door. That's 5 ways. But now, each of the other ones have to go through the same door. They've only got one choice now, so you end up with 5. So there's our probability. They use the same exit. 5 in 625, 1 in 125. Next part. What's the probability that A, B and C go out the same exit, but D goes out a different one? There's my answer. Where does it come from? Well, I'm thinking about D first, because actually the order the mice leave doesn't really matter. Same as when I was rolling those dice. It doesn't really matter whether I did them all at once or went bang, bang, bang. So in this case, it didn't matter the order they're leaving. So D, let's say they're the first ones to leave, and they'll go through any of them. There's 5 they could go through. But now, the next one can't go through that door. So remember, D is going through a different door to all the others. So there's 4 that they could go through. That leaves us 2 more to go, and they've got to go through the same one. All I've said is D. That's wrong, isn't it? Not the same one as D, but the same one as the other mouse. We end up with 20. So the probability, 20 on 625, 4 in 125. Well, what's the probability that any 3 of the 4 mice go out the same exit, and then the other one goes out a different one? All right, well, we just worked out the probability that D uses a different exit. But what we know is they all acted independently, but they were all equally likely. Therefore, logic tells me that the probability that A uses a different exit to the other 3 must be the same. The probability that B uses a different exit to all the other ones must be the same. The probability that C uses a different exit must be the same. So add them all up, or 4 times, doesn't really matter how you do that, we get 16 on 125. Okay. Oh, and the question kept going. What's the probability that no more than 2 mice go out the same exit? No more than 2. But this is where I now use the complementary idea, because if you think about what is the other situation, the other situation to no more than 2 would be more than 2. All go out the same exit, which we've worked out already. 3 go out the same exit, which we've worked out already. So why give ourselves more work? I'll just go 1 minus the ones we've already found, 108 and 125. So that was a nice little question. Covered all sorts of things there. So that was the basic counting principle where we start. That brings us to permutations. Basically, permutations is now when that order is important. It becomes important. So you can think of it as an arrangement of objects. So how we're actually going to arrange things. We're going to look at different cases. We have n different objects. And we're going to choose them from a set of n different objects. Basically, that just means we're going to use everything. We're going to arrange every object that we've got. How many ways can we do it? So I want you to imagine that over here in the corner, right, over here, right, there are n objects over here. I'm going to line them up across the front of the room. How many ways can I do it? Well, I'm going to go get the first object. There's n I could get. All right, over there you go. So go line up, will you? Good on you. Now I'm going to go get the next object. How many get? Well, now there's only n minus 1 to get. Now I'll go get the next object. There's n minus 2. And I could keep doing that, but because I'm using all of them, eventually there'll be one poor little object by themselves, feeling lonely. Okay, that's all right, you can come along as well. In you go. But there's only one choice. And look what we end up with. There's our n factorial. So it makes life really easy. If I want to arrange n things in order, there's n factorial ways of doing it. How many ways then can we get 5 boys and 4 girls? Line up. No restrictions. Well, if there's no restrictions, it's just 9 factorial. 5 boys, 4 girls, who cares? It's just 9 people. We've got 9 objects, people, line them up, 9 factorial. But now we put a little bit of a challenge into it. We say, no. We want to make a pretty pattern. We're going to go, the boys and girls are going to alternate. Always look after any restrictions in the problem first. Think about what is the restriction. And there is a restriction. There is a decision that needs to be made. What is the first decision that needs to be made? Over there in our corner, we have 5 boys, 4 girls. What is the first decision I have to make before that? It's not just who comes first. What are you going to say? Oh, no, there's nothing there that says, well, exactly. Because there's a different number of boys and girls, I have to start with a boy. Because if I select a girl, it will be impossible to make them alternate. So actually, you probably wouldn't write it down, but actually this should start with 1. Because that first choice is, which gender am I going to pick first? And there's only one choice. Now, if we had the same number, I would start with 2. Because my decision is, well, which one will I start with? Oh, I could start with a boy or a girl. So it'll be 2 times. But in this case, it's going to be just 1, because I must. There is no choice. Okay, I've made that decision. Now, I'll grab the boys. I'll just grab them. All right, you 5, go line up. There are 5 factorial ways of doing that. Now, I just go over to the girls. Girls, arrange yourselves, but just slot yourselves in between the guys, will you? Again, it doesn't matter. It's like the dice. It didn't matter whether I did it all at once or I did it one at a time. We get the same answer. 1 times 5 factorial times 4 factorial, 2880. Okay. Along comes the now logical question, what's the probability that the boys and girls alternate? And it becomes a very easy question to do because we now know the size of those spaces. 2,880 over, just imagine if we wrote out every possibility, be here forever. 1 in 126 is the probability. Now, different situation. They're still over there, they're in the corner. And 2 of the girls go, hang on, we'd like to be together, please. Yeah, okay. Look after the restriction first. What is that restriction? These 2 people have said, I want to be together. Okay. Well, you 2 sort yourselves out. Which order do you want to go in? Well, 2 factorials, 2 objects. But as far as we're concerned, you two are now one object. Now, link arms if you like, whatever you want to do, but you got to stay in that order. And what it now means is we're going to go, right, line up. But we're no longer lining up 9 people. We're lining up 8. Because these two are now linked together, they're one object. So 8 factorial ways of arranging that. And we get our answer, 8,640. Okay. That's if we use all of the objects. But what happens if we don't? We're only going to use k of them, and k obviously is less than n because n's the number of objects. We're only going to use some of the objects. How does it change? We've got our n objects in the corner here. We're only going to arrange k of them. So we go along, first decision is still the same, I need someone. Okay, go line up, will you? So that first person's got n. The next person, still n minus 1 I've got to choose from. Still n minus 2, but this time I'm not going to keep going all the way. I'm going to stop at the kth object. The question is, how many ways could I get the kth object? Well, if we look at our pattern here, when there was 1 object there was n. When there was 2 objects there was n minus 1. When there was 3 objects there was n minus 2. Therefore, logically, k objects must have been n minus k plus 1. Rewriting that to make it look more complicated, but actually it's a lot simpler. There we go. I've just multiplied by 1, by the way, because you'll notice the top and bottom of the fraction is the same. But what we end up with is n factorial on n minus k factorial. Let's think about that answer. N factorial. That was the number of ways of arranging all of the objects. What is n minus k factorial then? And that's the number of ways of arranging those objects that are still in the corner that I did not use. There are n minus k of them over there, didn't use them. So I divide out by all those possibilities because I'm not using them. So it's n factorial on n minus k factorial. There is a notation for that for permutation, npk. You guys are so much luckier than me because you got a button on your calculator that'll work that out. Some of these, it is going to be easier just to go n factorial over n minus k factorial and calculate that rather than use the p button. Let's do some of these questions. They love word questions. So because we like problems that involve words, let's look at the word problems. The question is, how many 5-letter words are possible? This question, there are no restrictions. Always a good question because it's going to be the bottom of your fraction in any probability question. Okay. There are no restrictions. Well, 8p5. I've got 8, I'm going to use 5 of them. The order is important. 8 factorial on 3 factorial, which is 8 times 7 times 6, which is 6,720. Hang on. Now let's make it fun. Of all these words, they must begin with P. Look after the restriction first. I must begin with P. All right, well, let's place P in our word. Well, there's only one spot I can put it. It's got to be at the start. So one way I can do that. Now, let's get the rest of them. I need 4 more letters, but I've got 7 letters now. So really, it's like saying, how many 4-letter words can I get from Roblums? Bingo, 840. P is included, but not at the beginning. Oh, and M, we don't like M. Nah, not going to use that letter. No way. Okay, look after the restriction. I'm now going to place P, but I've got 4 spots I can put P. It can go anywhere, just not at the start. Let's get the other letters. But this time it's 6p4 because I can't use M. So I'm now saying, how many 4-letter words can I get from Robbles? And that's 6p4. Notice, nowhere in here did it say, what's the probability of? Make sure you know what you're answering. Right? Sometimes they might just simply say, how many ways can this happen? They're not actually asking a probability question. So make sure you know what they're asking. 6 people are in a boat. The boat's got 8 seats, 4 on each side, and they're not particularly good spellers. Okay. What's the probability that Bill and Ted are on the left side and Greg is on the right? Now it's a probability question. Probability question, they haven't actually asked me for no restrictions, but I'm going to need that. That's going to go on the bottom of the fraction. So let's work that out. 8 seats in the boat. We're going to end up using 6 of them because 6 people are going in. All right, I know the bottom of the fraction is going to be 20,160. Okay, look after the restrictions. Bill and Ted only want to go on the left. Okay, well, 4p2. There's only 4 seats on the left. Going to use 2 of them. 4p2. Now, Greg says, well, I don't want to be with them. I'm going on the other side. Well, there's 4 seats you can go in, 4p1, and the rest of them go, hang on, what are these 3 on about? Who cares where you sit? There are 5 seats left. We're going to use 3 of them, 5p3, 2,880. So now we can answer the probability question, and it is 1 in 7. Let's have a look at this HSC one, a little bit more recent. Still a fair way to go, but a bit more recent than the last one. Sphere's got 5 coloured blocks. One's red, one's blue, one's green, one's yellow, and one is white. It creates little towers playing with the blocks. 2, 3, 4, 5 on top of each other. Get a lovely little tower. How many different towers that are 3 blocks high? I got 5 blocks. The arrangement's important because the colours would make different towers. So it becomes 5p3. There are 60 different towers we could make. Well, how many different towers in total? Well, 2 block towers. Notice I didn't do a 1 block tower because a 1 block tower is not a tower. Right? What's a 1 block tower? A block, that's right. It's not a tower. So we start at 2. Mind you, if you didn't realise that, they did tell you in the question. Where was it? She stacks 2, 3, 4 or 5. That doesn't mention 1. So 5p2, that's 20. Well, 3 blocks we just worked out. That's 60. 4 blocks is 120. 5 blocks is also 120. Add them all up. We got 320 different towers that we could have. Alrighty, let's have some outrageous fun.